So far we've reviewed all the type of integrals, two types of line integrals, two type of surface integrals, and we kind of compare them. Now let's see what theorems are related to what. As far as it goes, we don't explicitly use any theorems with the scalar line integrals. No theorems, and non-explicitly with the scalar surface integrals. Vector line integrals actually has a lot of, quite a few of the theorems are related to these. And so the first one that is related that makes the integration, the vector line integration easy is if f is conservative. And we know that we have at least two conditions that will guarantee conservative. That's when if curl of f is equal to 0 vector and f in the domain has no holes, or it's simply connected domains, and so for two-dimensional means it doesn't have any holes, or for three-dimensional means that doesn't something is not excluded, that is that goes through the entire 3-dimension basically. And so this makes the domain conservative, and if the domain is conservative, then again remember the notation of the vector line integral. This is going to be equal to f at r of b, that's the endpoint, minus f at r of a. This r of b and r of a usually are in terms of x, y, z, right? The output of r of a and r of b. And so when the parameterization is, when c is parameterized by r of t runs between a and b, and the little f is the scalar potential. And so finding the scalar potential, then you may have to find a scalar potential, and finding the scalar potential if f is equal to, sometimes a scalar potential is given to you. If f is equal to this, basically the three components of f, remember that p is going to be basically the derivative with respect to x of f. This one is going to be derivative partial respect to y of f. This one is going to be partial respect to z of f. So if I do the antiderivative, if I do p dx, q dy, and r dz, I should get all the terms in the f back basically. And sometimes those terms don't show explicitly because they are basically counted as a constant in there. So that's why we have C1, C2, C3 constant in here, and we compare for every term, common term, just put it in the function once. That's the important part of it. Don't count it twice because it's a common term, it shows up. Now, is there any other theorem that goes with this? Yes, there are at least two more that we can discuss. And so the other one is the Green's. So that was the theorem of conservative field, and Green's theorem. With Green's theorem, you're going basically around. That's why we call it contour. And this means contour. Sometimes it has an arrow that tells you either counterclockwise or clockwise. And so for Green's theorem, you want to have f dot dr with the counterclockwise is going to be dot dr. There we go. Is going to be a double integral of curl of f dA, and this is going to be, this is over C, which is closed and simple, and then you will have a D, which is the region that C basically encloses. Now, if you want to, this as you notice, oh, curl in the Z direction, this is a two-dimensional thing, and if you want to go to 3dim, it's still very similar to this, and that would be the Stokes theorem. And 3D, and then again you will have, and I cannot have the little arrow in there. Why? Because it's in 3D. In 2D there is a counterclockwise, clockwise direction. And I cannot have the double integral as in section. This one is the double integral in section 15.2 or 15.4, that sort of things. Here I cannot have that, so I will have a surface integral with the curl of f dot ds over the surface that C encloses, basically. And so a lot of times you don't see C in here, you see instead boundary of S, right? So the boundary of S. And so there's one little dot, and there's one little catch in here that the direction of the going around the surface should be should follow the orientation of the surface by a right hand rule. So you need a right hand rule. So the surface integral and the direction of the orientation of the surface and the orientation of the curve should follow the right hand rule. That's the thing. So all three of them somehow were related to the f dot dr. And if you notice, Stokes theorem is just a more generalized version of the Green's theorem, basically. It's easier to set up the Green's theorem. It's just all these counting, oh, am I doing surface integral? Am I doing regular double integral? That doesn't involve in there. So the last theorem that you want to use is related to the, so basically, Stokes theorem was both related to surface integral and the line, vector surface integral and vector line integrals. But the other two was just were related to the vector line integrals. Now, one more theorem at the end, and that's the divergence theorem. Says that the surface integral, and I'm going to go contour again because this is, you're thinking about a solid, W, and you're thinking about this surface that encloses that solid. S is the W is a solid, S is the surface enclosing W. And so basically the contour integral, that means that you go around the closed surface, S of f dot ds, the capital S. So this is the flux out of the closed surface is going to be a triple integral. This is a triple integral from section 15.3 of what is that? That's the divergence of f dv over w. So this one is the section 15.3. Now, what else is left? There are the stories with Green's theorem and holes that we didn't cover, and a little bit of a physical property that is going with this. A lot of times people talk about Green's and Stokes theorem as in, so you're basically summing the infinitesimal curl, and then that sum around the surface is going to be the rotation of the boundary of that surface. So the right hand side is sum of the little rotations, adds up to the rotation of the infinitesimal rotation, it adds up to the rotation over the boundary. And with divergence theorem is that you're saying that the stuff that gets out of the surface enclosing volume is equal to the infinitesimal divergence of the entire volume summed together. And then again, so you can Green's theorem is supposed to be a simple region, and basically the parameterization of the curve is supposed to be a simple closed curve, but it's also possible to apply the Green's theorem with what we showed with breaking the region into pieces and then have a hole in there. So you can have regions like this, basically, that this is the region, and then you will have two boundaries, and then you can add up the vector line integral on the boundaries, and if this is C1, for example, and this one is C2, let's see if the C2 is in the opposite direction, which is going to be in the counterclockwise direction, then you can add up C1 f dot dr plus C2 f dot dr. That's going to be equal to the double integral that you have on the right hand side, and that's over the area, shaded area. And if the direction of C2 is opposite or direction of C1 is opposite, you make it a negative sign instead of a positive sign, basically. And that's it with these problems.